This video is an attempt to grasp the unimaginable vastness, the space we found ourselves in, for better or worse, our universe. But let me start in an unusual way. Anyone who has ever played video games is familiar with the concept of a map, the navigable space available to the player. Maps can be tiny and unfinished, or massive and intricately detailed. Some even seem endless. For years, viral videos have compared the sizes of different in-game worlds. As you watch, you can't help but wonder, just how big are these worlds, really? One famous example is the Elder Scrolls II Daggerfall 1996. Its map spans about 209,000 square kilometers, almost the size of Great Britain. The game contains multiple large regions with distinct landscapes and around 5,000 cities. Some YouTubers have even tried to cross the entire map, spending dozens of hours doing so. Of course, such a huge world wasn't handcrafted. It was built through procedural generation, a system where algorithms with carefully chosen parameters create vast, believable worlds. Done well, the results can rival the work of human artists. Keep watching those comparison videos, and you'll discover that Microsoft Flight Simulator 2020 contains a one-to-one scale model of the Earth itself. But even that pales in comparison to Minecraft. Its procedurally generated worlds can be far larger than our planet, roughly half the surface area of Neptune. And still, this is just the beginning. In these videos, the scale jumps from Earth-sized maps to cosmic proportions. You see the sun compared to the map of Star Citizen. Then you zoom out past the solar system, past the Ring Nebula, past the pillars of creation, until you reach the map of EVE Online. At this point, the scale defies imagination. And yet, the journey doesn't end there. Elite Dangerous offers a one-to-one recreation of the Milky Way galaxy. And finally, No Man's Sky. In this game, you can explore 18 quintillion planets. How is that even possible? The answer lies in how these worlds are generated. True randomness is rare in games. It requires expensive hardware that draws on unpredictable physical processes like thermal noise or radioactive decay. Instead, games rely on pseudo-randomness numbers generated through mathematical formulas. Take Minecraft. Its creator, Marcus Persson, used an algorithm called Perlin noise, which produces natural-looking textures. In Minecraft, Perlin noise acts as a height map, forming the terrain. After the terrain is generated, additional algorithms scatter objects, trees, dungeons, mobs, according to certain rules. Water levels, for instance, never rise above 63 vertical blocks. Trees can't grow underground. Birches won't spawn in savannas, and deserts will never see rain. No Man's Sky takes procedural generation even further. Instead of blocks, its worlds are made of voxels, 3D pixels. The challenge for developers was that until a planet was generated, they couldn't predict whether a voxel would end up on a mountain or a plain. To solve this, Hello Games used a derivative of Perlin noise that let them preview landscapes before creation, making it possible to refine terrain features. With additional functions to warp and deform the noise, they produced coastlines, riverbeds, terraces, and plateaus landscapes that looked strikingly real, like satellite photos of alien worlds. And here's the most remarkable part. Despite its scale, No Man's Sky takes up only 15 gigabytes. That's because the planets aren't stored on your computer. They're generated in real time, every time you visit one. Everything is understood by comparison. Measurement is what allows us to consciously perceive the world. It seems to be a fundamental principle of human thought. How else can we explain our habit of translating an animal's age into human years? This evolutionary trait, our instinct to compare ourselves to potential rivals, also explains why videos that compare completely different things are so popular. And let's be honest, we're fascinated by anything that feels huge. A traditional map is just a projection of a landscape that helps you navigate. But in video games, a map is something more. Developers design entire cartographic systems alongside the virtual worlds themselves. This is, in a sense, a glimpse into the future of virtual reality. Before building a game world, developers must decide on its scale, limited by both money and technology. The larger the world, the greater the cost. That's why, in gaming culture, the word map has taken on a deeper meaning. When gamers say map, they often mean the game world itself, its terrain, textures, and objects. The map is the world, and the world is the map. Take Skyrim. In its map menu, you don't just see a flat piece of parchment. You literally soar above the world, gazing down at a miniature version of the entire realm. From this godlike perspective, the player feels like the one for whom the whole space exists. The ultimate expression of this design philosophy is found in strategy games, where you don't play as a single character at all. You become an idea, a society, a nation governing politics, economics, and territory through cartographic projection. Of course, every game world also has its limits, the weight of its files, the memory it occupies, the boundaries the developers impose. Even the largest maps eventually stop, and those limits shape how players act. Try to sail off the island in GTA 5, your boat sinks, your plane breaks apart, and if you're still in the water, a shark makes sure you don't get far. In the first Gothic, players are told right away that a magical barrier keeps prisoners inside the colony. Cross it, and your character glows with warning signs, then dies within seconds. These restrictions push players to focus on the existing space, to complete missions, explore, and experiment within the boundaries of the possible. But in Minecraft, or No Man's Sky, there are no such boundaries. The possibilities feel infinite, and that's what drew me deeper. After exploring the logic of these artificial worlds, I became fascinated by the ultimate comparison, the real one, the map, the world, the universe into which we were born. In this video, we'll ask, how is our universe structured? What lies beyond it? How do elementary particles, the building blocks of everything, actually work? What lies at the heart of the debate between idealists and materialists? And how do we explain the immaterial side of our own nature? Get ready, the most interesting part hasn't even begun. If this resonates with you and you'd like to support my work, please like the video, subscribe to the channel, and leave a comment. The universe is everything we can see, the endless expanse of space, the stars, the planets, the black holes, even our own Earth. You and I are parts of it too, but we'll return to our fate in this vast cosmos later. For now, our story begins here on Earth, a rare world covered in oceans and wrapped in an atmosphere stable enough to sustain life. The first stop beyond our planet is the Moon, just 384,000 kilometers away. Light takes a little over a second to travel that distance. If you tried to drive there in a car at 100 km per hour, the trip would last more than 160 days. From the Moon, Earth looks like a small blue-green marble hanging in a black void. It was here that humanity first truly realized how tiny our world is within the universe. From the Moon, astronauts could watch storms swirl across continents, hurricanes form and vanish, clouds drift across the oceans. For the first time, humanity saw its home from the outside, fragile, delicate, defenseless against the infinite darkness. Continue onward, and we reach the Sun 1 astronomical unit away, about 150 million kilometers. Light makes the journey in just over 8 minutes. But if you tried to reach the Sun in a jet traveling 900 km per hour, it would take you 19 years. Even within our own solar system, space is almost incomprehensibly vast. The Sun holds 8 planets in orbit, including Earth, along with dwarf planets like Pluto, countless asteroids, comets, and interplanetary dust. This whole system stretches to the edge of the heliosphere, a bubble of solar wind extending about 120 astronomical units into space. Beyond that boundary, we leave the solar system. In 1977, Voyager 1 was launched from Earth. Today, it is the most distant object ever created by human hands, more than 22 billion kilometers away. In 1990, from a distance of 6 billion kilometers, it sent back a photograph that would become iconic, a faint point of light known as the pale blue dot. Carl Sagan reflected on that image with words that still echo. Look again at that dot. That's our home. That's us. Everyone you love, everyone you know, everyone you've ever heard of, every human being who ever lived out their lives on it. The sum of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every loving couple, every mother and father, every able child, inventor and explorer, every morality teacher, every lying politician, every superstar, every greatest leader, every saint and sinner in the history of our species has lived here on a speck of dust suspended in a sunbeam. Our posturing, our imagined importance, the illusion of our privileged status in the universe, they all crumble before this point of pale light. Our planet is but a lonely speck in the surrounding cosmic darkness. In this vast emptiness, there is no hint that anyone will come to our aid to save us from our ignorance. Our sun is just one of hundreds of billions of stars in the Milky Way, a spiral galaxy about 100,000 light-years across. We live in the Orion Arm, roughly 27,000 light-years from the galactic center. And what lies at the heart of our galaxy? A supermassive black hole known as Sagittarius A. Sagittarius A contains about 4 million times the mass of our Sun, sitting some 26,500 light-years away in the direction of the constellation Sagittarius. It's an invisible region of space. Black holes cannot be observed directly in visible light, but we know it's there because of the way stars whip around it, as if tethered by an unseen force. In 2022, the Event Horizon Telescope collaboration unveiled the first image of its shadow, not the black hole itself, but the glowing ring of light from matter spiraling into it. This was the second black hole ever photographed, after the famous image of the black hole in galaxy M87 in 2019. Step back further, and galaxies themselves appear as immense islands of stars, gas, dust, and dark matter, all bound together by gravity. The Milky Way belongs to the Local Group, a cluster of over 50 galaxies that includes Andromeda and Triangulum. The Local Group itself sits within the Virgo supercluster, home to thousands of galaxies. And beyond even that, our galaxy is part of Laniakea, a structure 500 million light-years across, containing more than 1 million galaxies. Yet even superclusters are just knots in a grander design. Zoom out and you see galaxies woven into the cosmic web, a vast network of filaments made of galaxies and invisible matter. This unseen mass is what we call dark matter. It does not shine, it does not absorb light, but its gravity is undeniable. Stars at the edges of galaxies move far faster than they should if only visible matter were present. The missing mass, the unseen scaffolding holding galaxies together, can only be explained by dark matter. This breathtaking structure, formed through billions of years of gravity-shaping matter since the Big Bang, 13.8 billion years ago. And as we journey outward, we approach the very edge of the observable universe, a sphere about 90 billion light-years in diameter, called the Hubble volume. Within this sphere, light has had time to reach us since the birth of the cosmos. Beyond it, the expansion of space itself outruns light, leaving us blind to what lies farther still. And what exactly fills this observable universe? Strangely, only 5% is ordinary matter, the stuff of stars, planets, and people. Around 27% is dark matter, unseen but detectable by its gravity. The remaining 68% is something even stranger: dark energy. Dark energy is an invisible pressure embedded in the fabric of space itself, forcing the expansion of the universe to accelerate. Scientists first discovered it in 1998, when distant supernovae revealed that galaxies were speeding away from us faster than expected. Since then, dark energy has become the central mystery of modern cosmology. It was no accident that we began our journey by speaking of boundaries in video game worlds. For now, we too have reached a boundary, the edge of our universe. What lies beyond the Hubble sphere, we cannot yet know, but theories abound. There may be an extension of our universe beyond the Hubble volume. According to modern models, space itself may not be limited at all. It could stretch far beyond what we can see. What we observe is simply the region from which light has had time to reach us in nearly 14 billion years. But there are other, more intriguing possibilities. One is the inflationary multiverse, based on the theory of cosmological inflation developed by André Linde and Alan Guth. After the Big Bang, space expanded at unimaginable speed, and in the process, bubbles of individual universes could have formed. Ours is just one of them. Beyond our bubble may lie other universes, each with different physical constants and even different laws of nature. Another is the quantum multiverse, inspired by Hugh Everett's interpretation of quantum mechanics. In this view, every probabilistic event branches into multiple realities. All possible outcomes happen, but in different versions of the universe. These parallel worlds are not separated by distance. They exist side by side, unfolding in parallel with our own. If space is infinite, then somewhere in its endless expanse may exist worlds eerily similar to ours, histories replayed with small variations over and over in an infinite kaleidoscope. Then there is brain cosmology, drawn from string theory. In this picture, our universe is a three-dimensional brain floating within a higher dimensional space. Beyond it could be other brains, other universes, with their own unique properties. In some models, collisions between brains may even trigger new Big Bangs, giving birth to entirely new worlds. And finally, a theory as popular as the multiverse itself, the simulation hypothesis. Some scientists and philosophers suggest that our universe may be a vast computer simulation. In this scenario, the boundary of the Hubble sphere could be nothing more than a technical limitation of the system. If that's true, then the edges of our universe resemble the edges of an open-world video game. Having reached the horizon of our cosmos and stared into the abyss, we've expanded our sense of what might be possible. And now, it's time to dive deeper, not into the vastness of space, but into the smallest scales of existence, into the very building blocks of our universe. Since ancient times, humanity has asked the same question: what is the world made of? What forces lie at its foundation? Matter is what shapes everything from the smallest grains of sand to vast clusters of galaxies, from the spiral of DNA to the deep layers of the Earth. But the concept of matter was never given to us outright. It is the result of a long philosophical and scientific search. Over millennia, our understanding of the universe's foundations has changed radically, from myths and poetic images to strict logical theories, from the idea of primary elements to the physics of quantum fields. When the ancient Greeks first asked about the underlying principle of existence, they took a step that defined the course of European thought. This was the transition from mythos to logos, from explaining the world through stories and gods to seeking a rational, universal principle. Thales of Miletus believed that everything originates from water. At first glance, this seems almost naive. How can the world be made of water? But in context, the idea is profound. Water was the universal substance of life. It flowed in rivers, fell as rain, filled the seas, sustained plants and people alike. It could shift its form, becoming ice, steam, or liquid, yet always remained itself. Thales's claim was less about water itself than about the search for a single essence behind the diversity of things. His student, Anaximander, went further. He argued that no specific substance like water could be the true origin of everything. Instead, the foundation had to be infinite, boundless, and unchanging. He called it the aprion, Greek for the limitless. Aprion was not a substance, but an indefinite source from which all opposites arise: hot and cold, dry and wet, light and dark. For Anaximander, the world was born from this eternal principle, and to it everything must return. Anaximenes, continuing the Ionian tradition, proposed that air was the primary element. Invisible yet essential, air surrounds and penetrates all things. Compressed, it could become water. Rarefied, it could become fire. What mattered most was the method. The Ionian philosophers sought to explain the world in natural terms without invoking the supernatural. They searched for causes within nature, not outside of it. This was the first true step toward scientific thinking, the belief that the world can be understood if we uncover its logic, its patterns, and its hidden order. The next great turning point in the philosophy of matter came with Heraclitus and Parmenides, two thinkers whose ideas were utterly opposed. One argued that everything flows, everything changes. The other denied change altogether. Heraclitus became known as the philosopher of becoming. His famous phrase, "everything flows," captured his belief that the world is in constant motion. For him, fire was the primary substance, both matter and metaphor. Fire represented transformation, birth, and destruction, the eternal rhythm of change. It was Heraclitus who said, "You cannot step into the same river twice." Parmenides, by contrast, declared change to be an illusion. True being, he argued, is unchanging, eternal, indivisible, and one. If something exists, it cannot cease to exist. If something does not exist, it cannot come into being. From this reasoning, movement itself is impossible. He placed no trust in the senses, which deceive us, but in the mind, which alone can grasp truth. For the first time in philosophy, he drew a sharp line between ontological truth and empirical appearance, between reality itself and the illusions of perception. This tension would later echo in Plato's theory of ideas. After this clash of opposites, Greek thought turned towards synthesis. Philosophers, such as the Pythagoreans, Empedocles, and Anaxagoras, sought not only to define what matter is, but how it is organized. The Pythagoreans claimed that number is the basis of all things. To them, the universe was not built from matter, but from relations, proportions, and harmony. Everything is number. This vision foreshadows modern physics, where equations, symmetries, and mathematical structures describe the very essence of reality. Empedocles offered a compromise. All things are made of four elements: fire, air, water, and earth. What we call birth and death is only the mixing and separation of these elements. Nothing is born or perishes, he wrote, but only unites and divides. His view anticipated the later law of conservation of energy. Anaxagoras went further still. He imagined the world composed of an infinite number of tiny seeds, each containing every possible quality. Objects differ only in which properties dominate. In everything, he declared. This was the idea that every material contains traces of all others in different proportions. These three approaches, numerical, elemental, and seed, expanded the very meaning of matter. No longer just a single element, matter became a structure, a composition, a bearer of qualities. And then came the most radical leap: atomism. In the 5th century BC, Leucippus and his student Democritus proposed that the universe is built from countless tiny, invisible particles, atoms moving in the void. All the richness of the visible world, every sensation and experience, arises from their combinations. Democritus thus became the first great materialist. He imagined atoms as geometric forms. Iron was hard, he said, because its atoms were hooked together. Water flowed because its atoms were smooth and round. This was a remarkable anticipation of the microscopic structure of matter, confirmed only in the 19th century. For Democritus, the universe was not the product of divine will, but an autonomous mechanism. Everything exists because of the collision, movement, and ordering of atoms. The Middle Ages, however, shifted philosophy away from this ancient materialism. Matter was no longer seen as fixed and mechanical, but as something potential, a substrate awaiting form. This marked a profound change, from atoms as building blocks of reality to matter as possibility itself. For Aristotle, whose influence shaped much of medieval thought, matter was not an independent substance, but pure potentiality, formless in itself, yet capable of taking on any form. This duality of matter and form became the foundation of the metaphysics of Thomas Aquinas in the 13th century. Drawing on Aristotle, Aquinas argued that matter is potential, while form is act, the principle that shapes raw possibility into a concrete thing. Matter was passive, like marble awaiting the sculptor's hand. Yet within Christian thought, matter became increasingly secondary to spirit, especially under the influence of Platonism. For Augustine of Hippo, matter was associated with the sinful, chaotic side of existence, needing the divine logos to impose order. Matter, in his view, was a dark, passive substance set against the light of reason and grace. The 16th and 17th centuries brought a dramatic shift. The concept of matter was stripped of its theological wrapping and given precise, mechanical definition. René Descartes was among the first to define matter strictly as extension in space. For him, it possessed only quantitative properties: length, breadth, and depth. Qualities like taste, color, and smell were mere sensations of the mind. The world, he declared, was a vast machine, its workings reducible to particles in motion. Gone was Aristotle's form. All that remained was geometry and movement. Yet Descartes' worldview remained dualistic, dividing matter and spirit into two distinct substances. Galileo went further, proclaiming that the book of nature is written in the language of mathematics. Matter was no longer something to be described qualitatively, but quantitatively through numbers, equations, and measurement. Isaac Newton completed this revolution. Matter, for him, possessed mass and inertia, moving under forces described by the laws of mechanics. Gravity became a universal force, binding everything from falling apples to orbiting planets. For the first time in history, a single set of laws explained both heaven and earth. Matter itself was now seen as passive, subject to the push and pull of forces. Newton's mechanics could not only describe but predict the swing of a pendulum, the trajectory of a cannonball, the motion of the planets. Matter had become a mathematical entity, precisely measurable, rigorously testable. But by the 19th century, cracks began to appear in this mechanistic worldview. Matter, once imagined as solid bodies moving in predictable ways, revealed phenomena that Newtonian mechanics could not explain. Two revolutionary concepts entered physics: energy and field. The rise of electromagnetism was key. Michael Faraday showed that electricity and magnetism were deeply linked, though he lacked the mathematics to describe them. That challenge was met by James Clerk Maxwell, who in the 1960s unified electricity and magnetism into a single theory of the electromagnetic field. Maxwell revealed that light itself was an electromagnetic wave, showing that matter was not only particles, but also fields, invisible structures that carry energy across space. By the century's end, the discovery of the electron shattered the old view of atoms as indivisible. Matter was no longer fundamental. It had structure within structure. Physics and chemistry drew closer than ever before. And with Dmitri Mendeleev's periodic table, the hidden order of the elements themselves was revealed, predicting properties of substances that had not yet been discovered. The periodic table was more than a classification tool. It hinted that all substances obey deep, hidden laws. The 19th century closed with a powerful sense of order, but this order prepared the ground for a revolution. The 20th century would shatter the mechanistic worldview forever. The turning point came in 1900, when Max Planck studied the radiation of a so-called black body. To explain it, he proposed something unthinkable in classical physics. Energy is not continuous, but comes in discrete packets, quanta, multiples of Planck's constant. This bold hypothesis became the foundation of quantum theory. Just 5 years later, Albert Einstein expanded the idea to explain the photoelectric effect, where light knocks electrons out of metal. He suggested that light itself consists of particles, photons, whose energy depends on frequency. Light was both a wave and a particle at once, overturning centuries of certainty. In 1913, Niels Bohr introduced a model of the atom in which electrons orbit the nucleus in fixed quantum states. They do not radiate energy while stable, but when they jump between orbits, they emit or absorb light quanta. This explained atomic spectra and opened the way to the physics of the atom. By 1926, quantum theory transformed again. Erwin Schrödinger introduced wave mechanics, describing particles not as solid points, but as wave functions, a spread of probabilities across space. A particle no longer had a definite position, only the likelihood of being found somewhere. That same year, Werner Heisenberg formulated the uncertainty principle. It is impossible to measure both the position and momentum of a particle with unlimited precision. Determinism gave way to probability. Together, the works of Bohr, Schrödinger, and Heisenberg formed the Copenhagen interpretation. According to it, physical properties do not exist in a definite form until the moment of observation. Reality itself seemed to depend on the observer. The shift from classical to quantum physics was not just a new theory, it was a revolution in our very conception of existence. Matter was no longer a passive stage on which events unfold. It became a dynamic structure in which subject and object, observer and observed, are inseparably entwined. At this point, we must make a sharp turn. Having explored matter in depth, it is time to ask about the immaterial. When you look at a tree outside your window, do you truly see the tree itself, or only the image of it in your mind? When you smell coffee, hear your favorite song, embrace someone you love, is that reality existing on its own, or is it all born inside your consciousness? These simple yet profound questions mark the beginning of one of the oldest and most fascinating debates in philosophy. Idealism versus materialism. Two titans face each other. Materialism declares everything is matter, stone, air, you, me, even thought and love. All arise from particles, fields, energy. The world exists whether we perceive it or not. We are nothing more and nothing less than the product of matter at its highest level of organization. Idealism, by contrast, answers, everything is consciousness. The world is not out there, but in here. What we call the external is only a projection of the internal. We cannot step outside perception. Everything that exists for us exists in our mind. The debate began in ancient Greece. Plato argued for eternal, immaterial forms, the true reality. What we see in the dust of the streets is not real, only shadows, circles, beauty, goodness. These ideas are eternal, while material things fade away. Opposite him stood Democritus and Leucippus, creators of atomism. They saw not eternal ideas, but atoms in motion, indivisible particles colliding and combining to form stones, stars, and even souls. Thus, the first battle line was drawn, idea or atom. Centuries later, the radical idealist George Berkeley would claim, to be is to be perceived. A tree no one sees, a book no one reads, simply does not exist. And since the world does not vanish when our eyes close, he reasoned, there must be a higher consciousness, an eternal observer God. For idealism, meaning is what gives reality value. A painting is not just pigment, but an idea. Music is not vibrations, but emotion. Materialism replies, before thinking, you must exist. Consciousness does not emerge from nothing, it emerges from the brain. a material structure. Every thought is a biochemical process. Every feeling, an electrical signal between neurons. Matter is primary. It existed before us and will remain after us. Consciousness is only its byproduct, a spark from the machinery of the brain. If you want to understand reality, you must study matter through experiment, observation, science. Without knowledge of the laws of matter, there would be no medicine, no bridges, no telephones, no airplanes, no satellites. A material approach gives real results. Rockets fly, diseases are cured, enormous energy is harnessed, all because we accept that there is an objective world outside of us. At the heart of the clash between idealism and materialism is a single question. What came first, thought or substance? Spirit or atom? The idealist says, without ideas, there is no science, no morality, no love. Even physics begins with thinking. The materialist answers, without matter, there can be no thought. Ideas do not exist without neurons. Consciousness is born of chemistry and electricity in the brain. So, who are we? Spirits temporarily trapped in bodies, or bodies that learned how to think? Whichever way you lean, this debate touches every life. If you're an idealist, meaning and principle come first. You may value ideas over money, or see love not as hormones, but as something higher. If you're a materialist, you look for patterns, evidence, efficiency, plans before dreams, facts before hopes. In reality, of course, the two overlap. Idealists live more easily in material comfort, and materialists still find inspiration in poetry. Over centuries, both philosophies evolved. Idealism shifted from theology to the philosophy of consciousness, mysticism, art, even some interpretations of quantum physics, where the observer plays a decisive role. Materialism grew stronger through science. Newton, Darwin, Maxwell, Einstein. It explained stars and species, atoms and galaxies, and became the foundation of technology and medicine. In the 20th century, it took the form of Marxism. Being determines consciousness. Change the material base, and you change society. Perhaps the truth lies somewhere in between. Some philosophers have sought synthesis. Neutral monism suggests that matter and consciousness are two sides of a deeper, unknown reality. William James' pragmatism argued that what matters is not what things are made of, but how they work. We don't have to choose between idealism and materialism. Perhaps they are simply two perspectives on the same universe. For thousands of years, neither has destroyed the other. Each has its power and its weakness. Materialism gives us science, medicine, technology, but it risks leaving us without values. Idealism gives us art, morality, and meaning, but it risks detaching us from reality. The world is both matter and spirit, both atom and thought. We are creatures of particles, yet capable of dreaming, loving, suffering, and creating. And maybe what we truly need is not victory, but synthesis. Congratulations, you've reached the end of this episode. It was created by someone who thought and felt, typing on a keyboard, powered by electricity and digital code. It has a material embodiment, letters, glowing on your screen. But it is also an idea, a bouquet of meanings that will live on, as long as it remains in your mind. Thank you for watching.